Hello everybody, today we're going to talk about chapter 3, which deals with amplitude modulation fundamentals. We talked about this in class. This would be a nice review for some of you, and certainly will reinforce some of the concepts that we discussed that day that we went over it in class. So what we're going to talk about is the concepts of AM, amplitude modulation. We're going to go over modulation index and a percentage of modulation, which is what our lab is. We build an AM modulator and measure the percentage of modulation. Then we get into sidebands and what it looks like in the frequency domain, and power, and SSB, single sideband modulation, and finally classification of radio emissions, which we sort of suppress that. We're not going to focus on that too much. I will present it, however. Okay, so AM is a process of adjusting or modulating the carrier signal, which is the signal that you actually tune to on your radio, and it changes the amplitude or the intensity of that waveform with the modulated signal. The modulation signal, of course, is the voice, somebody talking, or music, or something like that. There's an envelope that is associated with that, that it's an imaginary line, which is best seen in this next slide after this. So here's the modulation signal. So again, this is somebody talking, or newscast, or perhaps music or something on the AM band, okay? And it forms this envelope as it modulates the carrier. Notice the carrier is a constant frequency. So this is your 580 WDBO on the AM radio dial or something like that, and that's a constant frequency. All right, and the modulation signal, which is what the sine wave is, and if you're listening to a sine wave, it's very boring, obviously, but it's certainly easy to see from an academic standpoint. So this modulates or changes the level of the carrier waveform with the modulating signal here. So here's the peak value of the carrier, this VC, and it's a algebraic operation that we'll look at here in a minute, how this all happens and how many other sine waves result from this modulation. Now there's two values. One is the two main important values. One is the peak value of the modulation voltage and the peak value of the carrier voltage. Now what we've got to make sure we don't do is to have the modulation voltage greater than the carrier voltage. Otherwise, distortion happens. And we're going to look at this in your lab. We're going to actually increase the modulation voltage to the point where it's larger than the carrier, and it's going to result in greater than 100% modulation, which is going to cause distortion. You'll be able to see that on the scope. Okay. Here's a little block diagram. We have our modulation signal coming in here. Here's the modulator, which we're going to build in the lab. Carrier signal. And this modulator results in this equation here. So this equation here is VC sine 2 pi FCT plus VM sine 2 pi FMT times the quantity sine 2 pi FCT. So the carrier signal is VC sine 2 pi FCT, right? That's just a simple sine wave, which has a peak value of VC and a frequency of FC, okay? The process of modulating that carrier results in this expression being added to it, which is the peak value of the modulation signal times sine 2 pi FMT, FM is the modulation frequency, times the quantity sine 2 pi FCT. So we multiply the sine part of the carrier signal to the modulation also, and we add that to the carrier. Now, as we went over in the lecture in class, the sine times sine expression can be changed using a little trigonometric magic into two cosine signals, okay, two cosine waves that are added together. And when you do that, you end up with sine plus cosine, which ends up being 3 sine waves, or a sine wave and 2 cosine waves. But cosine waves are the same as sine waves, just shifted by 90 degrees, right? Those cosine waves turn out to be the sidebands, okay? And we'll get into that in a minute. So the modulation index, going back to that, is the expression V sub m divided by V sub c, which is the modulation voltage divided by the carrier voltage. It's also known as a modulating factor or coefficient, degree of modulation. We often multiply it by 100 to give percentage of modulation. The most modulation you can have, of course, is 1 or 100%. That's otherwise distortion occurs. We use certain techniques called compression in the audio realm to keep that modulation voltage low enough or not to exceed VC to prevent that distortion. Okay, so the process of doing that compression will prevent the peaks of those values from going over the carrier voltage. We can also bring up the bottom end of that a little bit through some dynamic range compression. So there's always some sort of a compressor limiter on the microphone or the audio feed into the modulator in real practice, okay? So once again, it will cause distortion if it's greater than 1. It's garbled or unnatural sounds in the speaker, or distortion of video signals. So you won't be able to see your TV signal if you're using AM for TV. This is what it's going to look like in your lab, okay, on the scope. It's where the envelope is no longer really an envelope, it's more of a bunch of bubbles, okay? These parts here in between kind of separate, okay? And this is where the clipping's going to hurt. And so it doesn't look like an intelligible AM signal anymore. And we'll see this. I'll take a picture of that for your lab report, as well as the undermodulated or not fully modulated, and then another one which is fully modulated with an M of 1 or 100%. And here's how you measure it. It's we're going to have to take these measurements. You're going to have to use the scope cursor function on your oscilloscope and measure the Vmax minus Vmin divided by 2 to get your modulation index. Here's how you do that. Put the cursor right here. This is the signal you're going to see on your scope, by the way. You have to use 2 channels of the scope. First channel you're going to trigger on the modulation signal. The second channel is going to be the modulation, this signal. And you'll see this. It'll be very clear. And you can take the scope cursor function and measure Vmin and also measure Vmax and do this calculation, Vmax minus Vmin divided by 2. That's how you're going to get your modulation index. You're going to want to take pictures of that and show that in your lab report. So those 2 cosine waves that result from the multiplication of the 2 sines, those are sidebands, and we went over that in class. And one is the upper sideband, one is the lower sideband. And they're separated from the carrier in frequency by the modulation frequency. So for example, if you have a carrier frequency which is 500 kilohertz, all right, and you have a modulation frequency which is 10 kilohertz, you're going to get a sideband at 500 plus 10 kilohertz and 500 minus 10 kilohertz, or 490 kilohertz, and then another one at 510 kilohertz. Those are the 2 sidebands. And what I want to do is, when you get your modulators working in the lab, I want you to plug them into those brand new signal or brand new spectrum analyzers, and we'll be able to see those sidebands. Okay, so that's the goal. to hook up our spectrum analyzer and take a look at these sidebands. Here's what it looks like in the frequency domain, or the time domain actually. This is the time domain. I think we look at the frequency domain next time. But here's the envelope, okay? Here is modulation voltage here, that's A. B would be the lower sideband. C is the carrier. D is the upper sideband. Notice the sidebands are lower in amplitude. As a matter of fact, they're half of the carrier when modulation index is 1. It's exactly half of the carrier when you have 100% modulation. We're going to look at the frequency domain representation. So this is going to be our spectrum analyzer display. So it's a plot of signal amplitude versus frequency domain display. We're going to use our spectrum analyzer to look at this. The bandwidth is the difference between the upper and lower sideband frequencies. Now, understand that a real AM signal, a real AM broadcast, the frequency of the modulation is constantly changing unless you're just listening to a sine wave, in which case that's kind of boring, right? So if it's a broadcast, somebody talking, maybe a newscast or music, the frequency is bouncing back and forth, maybe, you know, between 1 and 3 kilohertz. AM broadcast on your AM radio, it's pretty limited in frequency. I think it's only limited to like voice frequencies, maybe 3 or 4 kilohertz, okay? And so the bandwidth isn't that much, but you have to accommodate the highest bandwidth there. So for example, if it is 3 kilohertz, then you're going to have upper sideband minus lower sideband, so you're going to get 6 kilohertz for the full bandwidth of the signal, okay? Doesn't always use that bandwidth, but that's what it is. So this is sort of a frequency, I guess it's a frequency and time display. If you turn it to the right a little bit and up, you'll just see the spectrum analyzer display. We have frequency going this way, we have time going this way. But on the spectrum analyzer, you'll see this as just a dagger right here. On the upper sideband, you'll see the carrier as another dagger, and then the lower sideband as another dagger. You won't see the modulation. It's way too low in frequency. We won't see that. It's actually not even part of the resultant signal. All we see is these 3 sine waves coming out of the antenna, if you will. This is embedded in all this stuff, okay? In the time domain, which is off this axis here, only time domain shows the AM waveform, the full AM waveform. We're going to talk about power in a minute. There's power in each one of these sine waves. The full power of the AM wave is the sum of all 3 of the powers. So here's an example. We have 980 kilohertz plus 5 kilohertz. That's the modulation frequencies up to 5 kilohertz. So I was wrong. I said 3 kilohertz is up to 5 kilohertz. Still not very much bandwidth, right? 5 kilohertz is almost voice. I guess it's 3 kilohertz is voice, but I guess they want to accommodate a little bit of music in there. So 980 plus 5, 980 minus 5, so 985, 975. Those are the upper and lower sidebands. The bandwidth is 10 kilohertz. 985 minus 575, or 2 times 5 kilohertz. That's 10 kilohertz. Pretty easy. Okay, we talked last time about Fourier transforms, right? And the fact that any square wave is an infinite number of odd harmonics of the fundamental. Well, that ends up being a pretty large bandwidth, right? So complex signal like pulses or rectangular waves using something called amplitude shift keying, which is a modulation technique. That results in a really wide bandwidth because you've got all of these harmonics in there, right? Well, up to this point, we've just been talking about sine waves as a modulation. Well, if you use a square wave, you got to accommodate all of those harmonics in the square wave. And that's why I wanted to emphasize the Fourier concept of complex of non-sinusoidal periodic waveforms. They are filled with harmonics, and that results in a really large bandwidth. Anytime you take a sine wave and make it into something else other than a sine wave, you're just adding harmonics, okay? So the bandwidth goes way up. And the extreme example of that, I suppose, would be the square wave, okay, where it has infinite number of harmonics. Now those upper harmonics are actually pretty low down because they do diminish in amplitude as you go up, but they're still there. So here we are. This is a frequency plot of a square wave. So here's the fundamental. Here's the third harmonic, fifth harmonic, seventh harmonic. So notice how they come down, okay, but they're still there. And if your system filters out these higher frequencies over here, excuse me, these higher frequencies, what's going to happen? Your square wave is going to become distorted. And that's why when you look at a square wave on a scope, oftentimes it looks distorted because those higher order harmonics are filtered out either by the scope or the scope probe or by the circuit itself. The circuit cannot support those higher order harmonics. If you filter out enough of them, okay, what do you end up with? You end up with a sine wave again, just the fundamental. And that's pretty common. That's a common technique to take a square wave, turn it into a sine wave just by filtering it. It's commonly done. So here's an ASK, amplitude shift keying type example. You're taking a modulation signal, which is a square wave. You bump it up in amplitude, you drop it down in amplitude, and so on. You end up with a very, very wide bandwidth signal. This is two examples, 50% modulation and 100% modulation, so it shuts it off completely. Either one's going to produce a lot of harmonics. There's another modulation technique. It's basically you're turning on and off the carrier. It's continuous wave, CW, and they used this back in the Morse code days. Don't think they do that. I think some hobbyists still do it, I'm sure, for ham radio, but yeah, it's also called on-off keying. Not real common anymore, but there is this thing called splatter which occurs, which is a byproduct of this really wide harmonic related bandwidth. And these sidebands get really out of control. So your system has to be able to accommodate this in terms of its band pass capabilities, or bandwidth capabilities, I should say. Okay, so as I mentioned earlier, that there's the three sine waves that come out of the antenna. AM antenna is going to be the carrier and the two sidebands. The total power is the total power of all of those. So it's the carrier, the two sidebands. Each signal produces power in the antenna. Okay, and the signal is the composite of all of those sine waves. Where's the information in the signal? Is it in the carrier? No. All the information is in the sidebands. But they're lower than the carrier, right, in amplitude. So most of the stuff coming out of the antenna isn't even used, right? The carrier is not really used. I mean, yeah, the receiver tunes to it, but you're really interested in what's going on in the sidebands. And here's the equation. Sorry, it's a little bit of an eye chart, but it's VC squared divided by 2R. Now this is the characteristic impedance of the system, typically 75 ohms or 50 ohms for an antenna system. How is it measured? The way other currents are measured, simply with an ammeter in line with the antenna. So this ends up being VC squared over 2R plus VM squared over 4R. That's the total power. There are some examples in the homework and examples in the textbook and some homework problems where you calculate this. Here's another set of equations which talks about the power. This is a simple one, PT equals PC plus M squared over 2. I don't know what these little question marks are. You're going to want to take these equations, all of them, and put them on your equation sheet and use them to do the homework problems and the examples in the textbook in preparation for the midterm exam. That's the only way you're going to be able to quickly get to them and know what they're for when you see this, these equations or need to use these equations on the exam. Okay, take my advice. So at 100% modulation, there's, like I say, half the power in each sideband, half the power of the carrier. But much less than that, okay, where there's a lot less than 100% modulation, most of the power is in the carrier. Either way, the total power is the total current squared times R. And as I said, R is the antenna impedance, typically 50 ohms or 75 ohms, depending on which system you're using. Now, the greater the percentage of modulation, the higher the sideband power, and the higher the total power, obviously. And so sideband is the power of the lower sideband. It also equals the power of the upper sideband. They're always equal, okay, in a typical AM broadcast. We'll talk about untypical stuff in a moment, but so that equals the carrier power times M squared divided by 4. Maximum power appears in the sidebands when the carrier is 100% modulated, meaning M is 1. Okay? So notice the power in the sideband. If M is 1, that means the power in the sideband is the carrier power divided by 4. So we have the carrier power, and then we have 1/4 of that on either side. Most of the information is in all of the information is in the sidebands, and they are 1/4 the power of the carrier. So that's not such a good deal. Very inefficient AM is. So how do you fix it? Well, just get rid of the sidebands and maybe the carrier, okay? That way, all the information is in just one of the sidebands. You got all the information you need, right? Well, there is some problems with that. You can use both sidebands. You can just filter out the carrier, and now you've got 2 sidebands. That's called double sideband suppressed carrier. No power is wasted on the carrier. The way you do that is what's called using a balanced modulator, which is basically a bridge circuit, a diode bridge. It's not widely used, it says here, because it's difficult to demodulate or recover at the receiver. And we have to be careful nowadays because the term difficult is not really as true as it used to be. And the reason is because we have some pretty fancy digital signal processors nowadays that can do really magical things. And they can take a single sideband received signal and recreate the other sideband. So for example, if just the upper sideband is broadcast, it can create the lower sideband, fabricate it, remanufacture it in the receiver, and in fact even recreate the carrier if it's known what it is. So these things are all can happen in modern receivers. Okay. Before, what we had to do is we had to actually adjust a knob and change the phase. It's all about it turns out the phase is something you cannot discern when you only have one sideband. So the intelligible signal, a voice, for example, sounds like a drunk Mickey Mouse. That's very interesting what it sounds like when you haven't got the phase of the single sideband signal dialed in. That can be done automatically now. So here's a little frequency plot of the two sidebands. So this would be a double sideband signal, sideband, sideband, and then the suppressed carrier is gone. Sometimes they put in, to make it a little easier for the receiver, a pilot carrier. So just a little, in other words, they suppress it not all the way, but bring it down to maybe a fourth or less of the sideband levels. That allows the receiver to tune into it, if you will, and then it can be amplified in the receiver, and once that's done, everything's back to normal. It's called a pilot carrier. Yeah, and the single sideband suppressed carrier is generated by suppressing the carrier and one sideband. And as I keep saying, one sideband is always necessary to convey the information in the signal. So here's some of the benefits of SSB. Spectrum space is conserved. Okay. And all power is channeled into one sideband. So it can produce a stronger signal that will carry farther and be more reliably received at greater distances. And the reason for that is because you've got three different frequencies coming out of a normal AM a full broadcast, not SSB or DSB or anything like that. So three frequencies. And the three frequencies go through the atmosphere, and sometimes they'll hit the ionosphere and bounce down to the receiving station. And when that happens, since they're three different frequencies, their phases get all messed up. It's really important that the phases of those three signals remain intact, the same as they were coming out of the antenna. But once they're reflected off the ionosphere, they get distorted. The phases get distorted. And so that can result in the receiver failing to discern the received signal properly, and you'll get distortion. So that's where this greater distances business comes from. If you're just transmitting one frequency, that's much better. Occupied bandwidth space is much narrower and the noise of signal is reduced. And as I said the other day, if there's one thing you leave this class with, there's a direct relationship between bandwidth and noise. Lower bandwidth means lower noise. Okay, so if you can reduce the necessary bandwidth or the required bandwidth of your receiver, your received signal is going to be less noisy, and that's great. Okay, and the process of this ionospheric interference, where you get the phases of the sidebands and the carrier scrambled a little bit, that's called selective fading. Okay. The disadvantages are difficult to recover or demodulate. And again, these days it's a little bit, not necessarily easier, but it becomes more manageable with digital signal processing techniques. And as I said, a pilot carrier is sometimes transmitted, which simplifies the receiver. You can use some analog techniques to actually put things back together. Yeah, the peak envelope power, we talked about this in class. Normally the maximum power of a transmitted signal using a normal terrestrial broadcast is about peak envelope, I call it PEP, peak envelope power, divided by 3 or 4. So we're only going a third or a fourth of what the system is actually capable of. All right. And there's one other VSB, which is often used in television transmission. HDTV, terrestrial broadcast, actually uses this vestigial sideband system. The other thing that the digital signal processors can do is embed other signals in the sidebands, just in the sideband. So for example, in your FM broadcast, which we're not talking about, we're talking about AM, but in FM, broadcasts, they can put some information, data, if you will, in one of the sidebands. And we'll see in a few weeks that FM produces a lot of sidebands. But they can choose one of those sidebands and put information in it, data, and that's what the radio data system is on your display for your FM radio. If a song is playing or broadcast, they'll put either an advertisement or identify the song or what the broadcast is in that data. Do some pretty clever things. Okay, lastly we have classification of radio emissions. So there's all these different techniques, right? Regular straight broadcast, there's double sideband, suppressed carrier double sideband, there's ASK. So here's some codes, if you will: A3F, amplitude modulated analog TV, SSB voice, FSK data. These are what these codes mean. I do not expect you to memorize any of these codes. In fact, this is what they are. I just want you to be aware of them, that they actually, the FCC has, and the industry, if you will, has a way of identifying or classifying these different radio modulation techniques or systems. So single sideband full carrier is H, single sideband no carrier is J, so on. And here's some more. Okay, so that's it for today, and we will be doing the lab for building a modulator, and hopefully we're all successful and enjoy that. I'm looking forward to it. Thank you.